Hello test subject. Assignment 1 is now art. Cake and grief counseling will be available on submission. Aperture Science recommends strictly following all posted directions. Your grade will be determined by an algorithm. We wish you a pleasant stay.
Hello everyone. As always, we are starting our week with a pioneer in the history of computing. In this case, it is Doug Englebart. Now, Doug Englebart and I do have a close personal connection. In fact, when I was 6 years old, I was dating his granddaughter in elementary school. I did not know she was Doug Englebart's granddaughter at the time, but I later found out and realized what a mistake I made when I later left the country to move back to Australia. Anyway, Doug Englebart is the founder of human computing interaction, which is the study of the way that humans work with computers. So for example, if you're asking the question, what impact does this technology have on people? Or what if I change the layout of Facebook, how does that change how people interact with it? Or what is the right way to design a user interface? This is the field that Douglas Englebart invented. In fact, this is quite timely as the largest conference in human-computer interaction is happening right now called CHI, Computer-Human Interaction. They've reordered the initials the other way around. One thing that Doug Englebart is particularly famous for is, what am I using? The computer mouse. In fact, you can see early versions of the computer mouse in Melbourne Connect. If you walk up and down the floors, there's a computer museum on each floor, and you can see an early mouse. And that was one of Douglas Englebart's inventions. In fact, he showed off a whole ton of inventions, including simultaneous word editing at something called the mother of all demos. And it's available to see on YouTube if you want to take a look. You can actually look through the different demos that Doug launched. At the end of last week, we started learning about queues, and we had two different ways of implementing our queue. The first way was an array, and the second one was using a linked list, a new data structure that we introduced. So for our array, just taking us a little back and doing a bit of a recap, if we wanted to insert something at the end, if we wanted to add a person to the queue, and we were using an array, how many steps would that take? Kylie, what do you think?
I think it's O of n.
O of n for an array. If we want to add something to the end of an array, how many steps does it take us? Let's say I know how many elements there are in my array. There are n elements in the array, and I want to put another element at the end of the array. What do I write in my code? Let's say the array is called A.
Oh, so that would be O1?
Yeah, O of 1, because?
Because you just insert it at the end.
Yeah, you know what the index of the end is. So Kylie says it's going to take us O of 1. All we'd do is we'd access A of n and set A of n equal to something that we want. So inserted end is actually pretty efficient for our queue in an array. But we have a bit more of a challenge when we're trying to add something to the front of the array. What's our challenge when we want to add something to the front of our queue using an array?
You have to move, like copy the array and move it.
Yeah, Kylie says when we remove the first thing, we'd have to copy all the other items down one spot so that they're now at the front of the array, so that what was the second item is now the first item. And how many steps does that take if we have n items in our array?
O of n.
O of n, because we have to copy each item once. And if there are n items, copy each item once. You do that n times, that's O of n. But we did have a way to get around this O of n time for removing something from the front of a queue, which seems like something we'd want to do pretty often. Okay, Lum, what do you think? How long would it take us to do, where did those slides go? Okay. How long would insert at end take for a linked list?
O of n.
Why would it take O of n? You got the right answer. When I create a linked list, what object do I typically keep track of? Let's go into my bag, and I'll pull out my my handy prop. what was this? Do you remember what I called this? This was the head of the linked list. So if I have the head of the linked list, and I want to put something at the end, what do I have to do?
Traverse.
Yeah, I have to traverse the list. And so I have to get from the head all the way to the tail. And if there are n items in the list, how long does it take me to get from the head to the tail? How many steps are there in the chain?
N.
Yeah, there are n. So if I have n items, I will have to go from the first item to the second item to the third item to the fourth item to the fifth item to the sixth item, all the way up to the nth item. And when I get up to the nth item, then I can add one to the end by attaching a new link there. So inserted end, unlike in our array, was O of n. What about adding something to the front, Lum? So if I know where my head is, how long does it take me to add something to the front?
O of 1.
Yeah, O of 1, because I know where the head is and I can put something right there and just rejoin it up. And that takes a constant number of steps. Okay, so we have this trade-off that we're making between how long our operations take for our array and our linked list, and maybe we'll talk about a little way to optimize the linked list a little further to get some better properties. So here's our data structure in C for creating a node, and just a collection of nodes is going to make up our linked list. This was our simplest way of implementing it. Now let's take a look at a few code demos to see how this works out in practice. We've done the in-person demos, we've seen some snippets. Now it's time to look at a full code example of implementing a linked list. And then of course, once we've implemented our linked list, making a queue is pretty simple. All we do is restrict ourselves to inserting things at the start and removing things from the end without allowing ourselves to touch stuff in the middle. Now of course you can break those rules, but then it's not a queue anymore. Okay, good, at least something is working today. So here I have my linked list code. And what I've done here is I've used a kind of interesting hash define. This is the first time we're seeing this. What I've actually done is I've defined a macro called insert at end. And remember, hash define works a lot like find replace. So it replaces whatever this is at the second part there with the first part. So if I have a function insert at index that goes into my linked list and inserts something at an index that I choose, let's say, I'm going to remove this for a second, and it inserts element for list x and element y. So y is the element I want to insert, x is the head of the list, and k is going to be the place that I want to insert it. That's going to be my insert at index function. So if I have a function list length, actually, other way around, y is the list, x is the element, and list length is going to give me the length of the list y. And so if I want to insert something at the end of the list, that's the same as inserting something at the last position and by using insert at index. So insert at index, I can say insert it at position 2, insert something at position 3, insert something at position 5. And so if I insert something at position n, where n is the length of the list, that's the same as insert at end. And why would I do this? Well, this syntax over here takes up more room on a line. It looks a little clunkier. And because insert at end is something that I'm probably going to do pretty frequently, I'm going to make a macro that enables me to very quickly replicate that second part of code by writing this first part of code here. So that's our first new thing. Then we have our node, as we saw before, pretty simple. It has some data for what's going to be the actual value. Remember, like the name of the person was the thing stored at that node. And then it's going to have a link to the next person or the next item in the list. We have our print list function. And how does print list work? Someone remind me if I want to print everything in a list. Just give me the pseudocode for it. Yeah. So loop over the elements and at each element, print the element. OK, thanks, Bronson. Let's check that out. There is print list. So start at the head and assign that to a temporary variable. Print the current element. So that's printing the data element. And then change your pointer to point to the next thing. Now, what's my loop termination condition, Bronson?
While p.
And so p is what kind of variable is it? What's the type? It says 2 lines above there on 108. There's a pointer. So when is a pointer true?
When it's pointing to something.
And when is a pointer false?
When it's not pointing.
And when is it not pointing to something? How do we know? What value?
When it's the null pointer.
When it's a null pointer, so when it's 0. And so this says, as long as p is not a null pointer, keep going. And so what happens is at some point, remember it was Nadine. Nadine was pointing off into the distance. And so if you remember from last class, when you get to the very end of the list, you're going to have someone that is pointing to nothing. And the way we represent nothing in C is with the number 0. And so p takes on that value 0. And so when you get back to the top of the loop, you'll evaluate while 0 is false. And so we just print a new line. So there's our print list function. That's the simplest one of our functions. We then have our push function, which we looked at last time. Let's do a quick recap. So what we're going to do here, we're going to create a new node in which to put our data. We're going to copy the data into that node. So our data is stuff. We're going to copy it in. In this case, we are making nodes that have strings, and so we're going to use string copy. And then we set the new node to point to the old head of the list, and then we return the new head. So again, this one is going to be easier if you draw it out. We went through this in more depth last lecture, so I'm not going to do the whole demo again. Now let's see if we can find an example of how to use this function. Oh, I actually haven't used it in this one. In this example, I've only used inserted end. So let's check out inserted index, because that's the other one we're going to need. So this takes an integer index, which is where in the list we're going to want to place the item that we've found. It takes some data that we want to find there, and a node t type. And I've called it p, but what would probably be a better name for p here? What is this thing? Typically, it's the head of the list. And so what I want to pass in, if I want to find something at like the ith index, I should pass in the head so that you can count from the head I elements in. If I pass it like the second or third element in, it's not going to know where it is. And so if I tell it to count 3 on from that, it's going to get the wrong answer. OK, so let's check out the code for that quickly. Again, we also saw this before, and it's similar to the code we just looked at. So create a new node using malloc. But right now, it's not attached to anything. It doesn't have any data. Its next pointer isn't pointing to anything. Copy stuff into it. Set its next pointer to null for the time being. And now we check what index it should go at. So if I insert something at index equals 0, where am I putting it? Where am I putting the new item? Who said that? Yeah, Agreb. It goes at the head if index is 0. That's the same as push. So I probably didn't need my push function. What could I have done instead? I just talked about this a minute or two ago. Let's scroll up a little bit. What could I make that would allow me not to have to rewrite a whole bit of code for push? Yeah. Yeah, I could do a hash define. So let's do a define push. And let's see what push took. It was, x and y. And then this is the same as insert at index x, y, 0. So then I could delete all the code for push and it would work perfectly fine. Remind me your name again.
Oh, Afan.
Afan. It's been a while since I've asked. OK. So let's go back to it. So that's if index equals 0. Now what if index doesn't equal 0? Then we're going to have to traverse the list going index steps in. So if index was 0, I didn't have to go anywhere. But if index is 2, I have to go 1, 2 hops, and then do the insert again. Now this is different than if I was just inserting something at the head. Why is it different? Where's Charlene? Back there. OK, why is it different if I insert something in the middle than if I insert something at the head? What extra thing do I have to do? In the middle of the list. So if I'm at the start of the list, how many people am I connected to? If I'm the first person in the list? 1. And if I'm in the middle of the list, how many people am I connected to? 2. Because there's a pointer coming from the person before me, and there's a pointer going from the person after. So if I insert something at the head of the list, how many new connections do I have to change? At the very start, if I'm a new node and I want to connect myself to the start of the list and be the new start, how many links do I end up with? You said it before. 1. And so if I want to insert myself in the middle of the list, how many links do I need to fix up? 2. Because I need to make sure that the person who's before me now points to me instead of what used to be here. And I need to make sure that I am pointing to the next person on in the list. So let's take a look at this in the code. So first, get to the right point in the list. So for I equals 0, up until you get to the index, just keep going to the next. Wait, there might be a bug here. What's a possible bug? What happens if I set index to be something larger than the length of the list? What will my program do? You said that? Fun. Yeah, it segfaults. Why does it segfault?
Because you're going to an area that you aren't allowed to go.
Yeah, so when I get to the end of the list, let's say there are 3 items in the list, and I say insert at index 5. I get to the third element, and then I do p equals p dot next, and now what's the new value of p? At the third element's the last one.
It wasn't initialized, so it will
Careful, it is initialized, but what should it be initialized to? Well, it's pointing to nowhere, and we talked about this before. When you're the last item in the list, you should point to what value? Who said that? Yeah?
EOF, right?
Not EOF. EOF is for files, but same kind of idea. Michael?
Point to the null pointer which you can't access.
Yeah, you make it 0, so it's a null pointer, which means what the value of p after getting next after the third element, which is the last one, will be 0. And then what happens is you try and dereference 0 by next time you go into the loop, and you do 0.next. But you can't dereference 0. 0 is the null pointer. That gives you a segfault. OK, so now let's assume a fun question. OK. So let's say we have element A points to B, points to C, and then C will point to the null pointer. And so we go through the loop once, we go through the loop twice, we go through the loop 3 times, we go to the loop 4 times, and that's all fine. And then what happens is we try and do 0.next. And when we do that, that's when it segfaults, when we try and access that. It's actually a really good exam question, is how many loops will this thing do until you get a segfault? And it's easy to be off by 1. Maybe I'll tell John Jong to put that nasty one in for you, but you're in class, so you already know it. So here we just fix up the 2 connections. So we set our new thing to point to the one that should be next in the list after that index. And we also make sure that we fix up what the guy before us was pointing to, because he should point to us now. Then we're done. Now let's look at an example of us actually using it. So here I have added a few students into my linked list. Young, Nash, Flo, Rose, and all the Mings. Did I spell Ming correctly? Oh, Min. For all of you? OK. Let me fix that. Didn't have time to get the spelling. OK. So let's compile this bad boy. And see if it works. So here I have created a list of length 8. You'll see if I look at who's in the list, it's Nick, then Young, Nash, Flo, Rose, and then all 3 of the Mins are added. And then what I can do is 1 by 1 remove the nodes from the front of the list. And we'll do the removes in a second. And each time be very careful to note that I'm setting the new head to be what pop has returned. And so let's look at our implementation of pop. We did that last class, but we should look at it one more time. So how do we remove something from the front? So the first thing I do is I create a new node to save a copy of an old node, and we'll see which node we save. We save the old head. Then we go to the new head, which is the old head's next pointer. Then we free the old head, and we return the new head. Why did I need to save the old head?
This is a bit of a tricky one. What was the lease?
No. Kylie? Kylie, sorry. Yeah.
Because you want to know the address of the old node, so you can do it.
Yeah, remember for every time we've allocated something, we also have to free it. And if I destroy the link to the old head and I forget the variable, that doesn't mean I've freed it. I have to free it explicitly. Just disconnecting it from the list doesn't free it. But if I hadn't saved old, let's say I comment out these lines of code, and now I try and free, well, I don't have something to free now because I've already changed what P is. I've changed P to point to the next thing, and I no longer have remembered what the old head was. So in order to remember the old head, I need to save a copy of it in this function. And that's it. And by returning the new head, I let my main program know, I let my main function know what the new head is, and then I can save that so when I do future operations on the list, I can use this new head. Okay. Let's look at another example. There's our basic code, but this time I've made one that has an intentional error. Now let's look just at the main function. Let's look here. Seems I might have accidentally made one that works. What this program should have looked like, this will make the bug a little too obvious. Okay, I just described what the problem with this is, but we'll go for a question anyway. What do we think? Why can't I just write that? Josh, you look very eager to answer.
But you haven't changed the value of head, so what are you popping? Like, that's not a thing anymore.
Well, I'm still popping it, so the actual list will have changed in memory.
The second and third times you're popping.
Yeah, the second and what have I done to that old head?
Gotten rid of it.
By gotten rid of it, what do you mean? I freed it. Yeah, so I will probably get a seg fault because head now refers to some memory that doesn't belong to me. I will make sure that next time I don't leave the correct answer sitting in there. And so in better push pop, here. Actually, I think I might have, the bad one might still be bad. Bad, let's take a look at, you'll see when I did push, I didn't update head. Yeah, so there's the bug. I didn't update head when I was using push. So I was right, I did make a mistake in my code, just not the mistake I thought I'd made. And so what this should have been is where head equals push, et cetera, so that I update the new head every time. Now let's try give bad push pop a run with what it was before with those in there. Okay. There we go, and then I get an assertion failed at pop because my list is now all mucked up because I haven't actually updated the head pointer. And so I've started to point to non-existent elements. Okay, now let's look at another example with a bug. This time, I have a memory leak. So let's take a look at my insert at index function. Let's see if you can spot the bug. Okay, actually it is in free list. So what I've done here is I have my functions pretty much as before. I have insert at end. Then I've done head, I popped the head a bunch of times. And then at the end, when my program is, when I'm done with the list, I need to free all the memory in the list. So let's look at what I'm doing here to free the list. And there is a mistake here, but I'm going to rely on you to tell me what it is. I'll describe the logic, and then you can tell me what I've done wrong. Now remember that our nodes look like this. We have some data, and data T is a name T type, and a name T type is a char star. So every time that I am making a new, that I'm going to make a new node, let's take a look at making a new node. I'm going to malloc some data for the node. I'm going to malloc some space for the string that I'll put in there, depending on how large the string was. And then I'll copy the value in, etc., and make the whole node. So I've got two mallocs here. I'm mallocing for the node, and I'm mallocing to make space for the string that's going to be there. Then I'm copying the string in. All seems like stuff we've seen before. OK, let's go to my free list function. In free list, OK, I've got a variable to keep track of the old head so that I can free things, or the old node. I'm going to start at the head. I'm going to save the prior node. I'm going to save the next node, and I'm going to move to it. And then I'm going to free the old one. And when I'm done, I'm going to return p. And what should p be when this function ends, given that I'm trying to free the entire list? Null. Should be null. The last element should point it to null. But there's still a bug here. In fact, I'll do you one better. There is a memory leak here. And I'm going to leave you about a minute to think about it on your own before I'll take an answer. So how many mallocs did I make when I do when I was creating a node? Do you remember?
I think it was 2.
It was 2. And how many frees am I doing for every node here?
Just 1.
1.
Yeah.
So what 2 things did I malloc? I'll scroll up back to the code in a second, but let's see if you remember.
One was something, one was a string. The second one was a string.
Okay, so I had to malloc the node itself, and then I had to malloc for, you just said it, for the string, because each node is going to contain a string, and we're allocating some memory for that string. So let's look up there. When I insert a new node, I'm going to malloc some space for the node. I'm going to malloc some space for the data. How much space? So I'm going to figure out how long the string is and make room for it on the null byte. OK, now let's go back to our free list. What am I freeing here? Freeing the node. So what have I forgotten to free? Yeah, I've forgotten to free the data within the node. So this is a memory leak. Let's say I run this program over a long time. I make lots of lists. I put in lots of strings. Over time, those strings are still going to stay in the heap because I've never freed them. And so even though I've destroyed the list, I've only freed the memory for the nodes, not for their contents. So now let's turn this over to Ed. You can see me using ChatGPT to make linked lists over there. There we go, workspace. So let's call this one bad 2. Now, what tool do I use if I want to find memory leaks? What was the really good tool? Does anyone remember?
Which operating system is that?
This is on Ed, so it's running Linux.
Valgrind?
Yeah, Valgrind. I have up the top here the command I've even put in the program for you. So let's first make the program. Yeah, I will do that in a second. I'm just going to compile it first. OK, that should be more or less visible. Maybe let's go 1 out. Now I'm going to run this Valgrind command, and we'll make sure you all get access to it. And I'm going to run it. Oh, that's Algrind. OK, Valgrind says I've definitely lost 24 bytes in 5 blocks. So let's look at how many nodes I've made. I've made 1, 2, 3, 4, 5. So it makes sense that there are 5 different locations in which I have lost some stuff. OK, so lost 24 bytes total. What's the 24 bytes referring to? Someone tell me? Yeah, the 5 strings in total would have contained 24 bytes. So let's see. There's 4, 4, 4. Liam, quiet you. 3 and 4. That doesn't add up to 24. It adds up to 19. What have I forgotten? Thanks, Liam. Come on. What have I forgotten? Yeah, I've forgotten the null bytes. So for each of these, I had to allocate a null byte along with all of them. OK. Now it's going to give us some more information. Let's scroll up. There's probably going to be some things we don't understand here yet. OK, here we go. 4 bytes in 1 block are definitely lost, OK, at malloc, by insert at index, by main. Now, depending on what I compiled this with. If I add the -G flag, it's now going to insert extra information into my program so that debuggers and analysis tools can actually give me line numbers and more detailed information. So I'm going to run this once more. There we go, I've run it again, and now let's scroll up and see what it's report. Oh, now I've got line numbers. It tells me where in the program things are happening. So let's go up to the first report. It says it's lost something that was originally mallocked. Okay, well, that's not useful information to us. But it also says that malloc was called by inserted index on line 76. So it says that this malloc function never had a matching free. And in fact, it gives us some more information as well. It tells us where the inserted index function was called as well. And it says insert index was called by main at bad.c line 51. So bad.c line 51. So this particular report is referring to the memory for flow that was lost. And so if we check, that's 3 letters plus 1 for the null byte. That's 4 bytes. And so this is what we call a partial stack trace. Now remember, we've talked a lot about the stack before. That's where you put variables, but it's also you put functions on top of one another. When function A calls function B, function A is on the bottom, function B goes on top. When function B calls function C is now the top of the stack. When function C calls function D, D is there, and so our stack looks like A, B, C, D. And so if we look at our stack trace here, we see function A, main, function B, inserted index, and function C, malloc, all building on top of one another. And so you can read the stack trace to figure out where your program is going wrong. And sometimes it might be that just looking at the one underneath malloc won't be enough, and you'll need to go back one more step and figure out, okay, which of the mallocs was it, and what condition did it happen? And then you can go further up the stack trace. And so Valgrind, while you may not be using dynamic memory for assignment 1, unless you're feeling particularly brave, as you start running into seg faults, this tool and address sanitizer, which we showed in another lecture, will become your best friend because they'll enable you to automatically figure out why your program is going wrong. So some signs that indicate that it might be a good time to try this tool. Does your program seg fault? Does your program terminate, but you can't figure out why and it doesn't produce any input? It might have crashed without saying the word seg fault. Does your program produce different output every time you run it? Does your program produce gibberish that doesn't look like anything that you would reasonably expect? All of these are signs of memory corruption or memory segmentation faults, seg faults. And Valgrind and Address Sanitizer are 2 really good tools to spot it. Okay, so we've seen a whole bunch of functions now. We've seen bad string. Let's look at the better version, at the fixed version. In the fixed version, let's see, print list, push, push, push. Where's my free list? There we go. All I've done now is I've added an extra free statement to free the data that was mallocked, to free that string that was mallocked. But I also have to do it before I free the node itself, because if I free the node itself, then I can no longer access its data member, and so that's too late. So this would result in a, what would that cause? Seg fault. So there's better string, and that is our set of linked list demos. Okay, so we mentioned that insert at n takes O of n time for this implementation, because we have to traverse the list to get to the end. Now, someone who doesn't already know the answer, and I'm looking at you, Ahmed, how can we make this faster? We've already talked about this once in class. How can I make inserted end O of 1? What extra piece of information could I keep track of? Michael, you've already answered today. Victor, how do you feel? Sorry.
Sorry, what was the question again?
So in order to insert something at the end of the linked list, I had to go follow the link, do that n times until I get to the end, because I was only keeping track of head. Is there an extra piece of information that I could keep track of to insert something to the tail quickly?
How long your linked is?
Well, if I know how long it is, I still have to go all the way from the start to the end. But you're on the right track. Instead of keeping track of how long it is there another variable that I can keep?
The tail?
Yeah. I can just keep the tail in memory. And that way I can jump directly to the tail. I can't go backwards because our linked list only has nodes forward, but I can go directly to insert something at the end in O of 1. Now, I have another question from this. So I just mentioned something interesting, that I've got a really fast way to get from the head to get to the head and get to the tail. Let's say I have a linked list of length 6, and I'm using, what's the smallest number of steps? Sorry, a linked list of length 10, and I want to get to element 6. How many steps, Angela, does it take to get there? It takes 6 steps. But if I'm keeping track of the head and keeping track of the tail, what's a better way to get to the 6th one? I could go from the end, but what's the problem? How do you go from the end? Because we've only got a pointer to the next thing. So how can I solve this problem? How can I modify my program?
You could, I don't know, you could figure out.
Okay, so what would turning it around mean? So I've got a pointer to next. What would I need?
A pointer up.
Yeah, exactly. That's a great idea. So I can add to every node, not just a pointer to next, but a pointer to, and let's call that previous. So this is called a doubly linked list. So every node in our list is now going to have a next and a previous, and then I can use this to get to elements that are in the middle of the list faster if I know the length of the list and I know the index at which I want to access it. So that's a bonus tool for you to use if you want to experiment with it. And what about pushing? Well, while we were talking about this, how long does pushing something in a linked list to push something to the front take? This is an easier one. If I want to add something, if I want to make a new head of the list, how many steps does it take? How many steps down the list I have to go? N would get me to the end of the list. If I just want to put something at the start, yeah, just one, so it's O of 1. Okay, so this has gotten a little complicated. Let's help you out for the rest of the semester, and we will provide you some ready-made code to help you out instead of implementing your own linked list. I will say that implementing your own linked list is very instructive. It's a great learning tool, but we don't necessarily expect you to do it. And so what we have for you is I will show you 2 different versions. This is a version that you won't end up using, and that's a little annoying to use. It's the one I've been working with before, where I have to always set the new head as the outcome of my operation. So I have to do head equals pop head. So that's annoying. Instead, what we can give you is we can give you a version where there's an actual list object. And a list object has a head, it has a foot, and we've given you a whole bunch of functions, our inserted head, inserted foot, get head, get tail, all the different functions you'd want, and then we can start using it. So what we're going to do now is we're going to include our list options file. Now we'll talk about better ways to include things later, but for the time being this will do. And then we can use our functions. We can make an empty list, and this will be our list object. And now we can do all our operations that are fairly well cleanly and easily documented, inserting at different locations, getting the head, getting the tail. And so this is available for you to use within your own code. Just make sure that you cite the fact that you're using the pre-provided code. So this is a summary of everything we've learned about lists and queues and arrays. If we are trying to access the kth element of an array, well, of course, we can do that quickly. If I want element I of an array, I do like AI. If I want to access the kth element in a linked list using pointers, then it takes me k steps because I have to traverse. Or if we're doing Angela's special way and we know it's of total length L, then I can go backwards that many steps. But still, it is going to be dependent on how far through the list the element is. To push something with pointers, it was super fast. We know where the head is. Let's just put something there. For arrays, we needed to move everything else along when we add something new to the start. Likewise with pop, when we remove something from our array, then we need to copy everything. But for our pointers, we can just remove the first thing and then insert at end. Inserting something at the end of an array was really fast. We know how long the array is. We just insert something at the end. Likewise, for our linked list, if we keep track of the tail, we can also do it in O of 1 because we know where both the head is and we know where the tail is. We can jump right to the tail and insert at end. And then insert at kth position, it's O of n copies for an array because we have to move things over to make room for the new one. And for pointers, it's O of n individual accesses because we have to traverse to that point in the linked list. Okay, so now we've got a whole bunch of different ideas here, different abstract data types. We've got lists, stacks, and queues, and these are all abstract data types. You can make a stack or you can make a queue using either linked lists or arrays. And in fact, you can also make a linked list in different ways. You can use dynamic memory in malloc, or you could even make a linked list that uses arrays, but then we have to remember that because a linked list is using arrays, we're going to get the performance of arrays and not the performance of pointers. So linked list describes the idea, and almost always when you make a linked list, you make it using pointers because that's more efficient and gives you all the benefits of making a linked list, but you don't have to. It's an idea of how to join things together, and you can implement that idea in C using either pointers or using arrays, which is why these are abstract data types. They're conceptions of how to organize data that we can then make using different tools in our toolbox. And the core idea here is that we want to separate out when we need to put something into our data structure, when we need to put something into our program from the time that we actually need it. So we don't want to have to think about, okay, was the thing added early on, was it added late on, how do I have to arrange my data structure to accommodate for the fact that some are going to be earlier and some are later? You don't want to care about that. You just want a data structure that you can get what's at the front and put something new at the end, and that's all. And that is why abstract data types are powerful. So we have one more idea that I want to touch on today, and this is polymorphism. So right now I've been using a queue or a linked list that deals with strings. And remember, this is why I had the annoying double free thing going on. But in fact, what we'd ideally have is we'd have a data structure that's polymorphic. That means it works with multiple, morphism types. And so even if we decide to use an int instead in our linked list, we want code that'll very quickly and easily allow us to use both. Now, getting this to work really nicely in C is a little tricky, but at least conceptually, you can think of it like some of the vending machines on campus now. The vending machines, the basic idea here is money in, snack out, but we want it to be able to accept different types of money and still do the same operation. The same basic idea of money in and snack out. Whether the snack is a sugary drink or a chocolate bar, it should still give us a snack. And regardless of whether the input is cash or credit card, it should still take money in. And so you can think of this as a rough analogy to polymorphism, to what we're trying to do. So in computing, we have a few different ways of thinking about polymorphism, and already we've encountered it a few times in this class. We've encountered it in sorting, where we have sorted numbers, we've sorted strings, and we could even imagine sorting presidents. Although for sorting presidents, we're going to have to define what it means to sort a president. So we could say sort in order of longest term in office to shortest term in office. And over there in that corner is William Henry Harrison, who was the president who had, I believe, the shortest tenure. He gave an inauguration speech in the freezing cold and rain, and 2 months later died of pneumonia. In fact, I used to be the librarian of the William Henry Harrison Presidential Library, and I will leave it there with that fun fact for today, and we'll carry on with a new data structure next week, and John coming to you with assignment details tomorrow. Thanks, everyone.